Hello, adventurers, and welcome to the last video on our Floor 8 trees. In the first video, we added the capability to build and measure the trees via the add child, count, and height methods. In the second video, we had two walks established. We had the pre-order and the level order. So we handled breadth first search and depth first search. And our self-test on our tree has phases 1 through 6 being green. Now, today is going to be our last method that we'll implement, which is going to be findFrom, which is a recursive search, which will allow us to green phase 7 for our self-test on our tree, and it will light up lineage. The public lineage is already written. It calls findFrom, then walks parent pointers to the root and reverses. Now, the only thing that we're going to owe here today is implementing the search. Now, findFrom has to check nodes one by one because a general tree has no ordering. Searching it is no faster than going and using Scrivener McCown's floor 1 flat list. That is exactly the problem that the next floor, which is going to be on binary search trees, exists to solve. And so it's kind of the on-ramp to floor 9, so to speak. So let's go ahead and build our executable, and we'll kind of set the stage for where we're at right now. So we'll do our self-test on our tree, and you'll notice that all of our phases are green except for the very last one. And then you'll also notice we have our lineage command where you can type in lineage and then pass in a name, and it will show the root to creature classification path. So if I said I want to know the lineage for the lich, you'll say lich is not in McCown's catalog. Okay, so we can build it, we can measure it, and we can walk it two ways. What we can't do is ask it anything. Okay, you notice when we say lineage lich and it says lich isn't in the catalog, but you know lich is there because we saw it in the last video. The lookup lies because our findFrom method is stubbed right now. It returns null pointer for everything, so lineage thinks nothing is found. So one method left, and it's going to be in the hero/tree header file. Okay. So let's go ahead and let's get to it. Okay, perfect. So we need to go down here. Okay, so we're going to need to implement this, but I did want to talk for a quick second about lineage here. That's pretty good. Okay. So lineage is done here, and let's read through it. It calls findFrom to get the node. If nothing's found, it returns an empty path. That's the it's not in the catalog case, not a bug. Otherwise, this right here is going to be our first video's parent pointer finally paying off. We start at the found node and follow parent, 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 all the way up to the root, collecting names. And then we reverse it because we collected them leaf to root and want root to leaf. The walk up is free because add child set every back pointer. All that's missing is the walk down to find the node, and that's going to be our findFrom. Okay. So let's go down here to our findFrom, which is right here. So notice we take in a node here and a value. So what we want to do is have our guard. So I'll say if n is equivalent to null pointer, we'll return null pointer. There's our guard. And say if n accessing the data is equivalent to the value we're looking for, we'll return n. Okay. Then we'll do our loop. So for standard size t, I is equal to 0, I less than n accessing the children size. Then we'll say plus plus I. We'll pop into our for loop, and I'll say if our const node pointer hit, We'll say equals findFrom. We'll say n will access our children at the ith index and look for the value. We'll return back our hit if we find it. Otherwise, we'll step out of that loop and we'll return back a null pointer. Okay. So the skeleton that we encountered in the first video for this floor is going to return here for us one more time. Our base case is a null subtree holds nothing, so we return null pointer. Then check this node. If its data matches, we're done, return it. Otherwise, we ask each child subtree in turn, and here is an idiom worth pausing on. If const node star hit equals findFrom child value, return hit. Okay. So we search the child. If it reports a hit, return that hit immediately. Don't keep looking. If no child finds it, fall through to return null pointer. That early return is what stops the search the instant we succeed. So let's go ahead and let's build this now. Okay, so we'll say self-test on our tree. Ooh. Man, I messed up my spelling twice. There we go. It's nice to get all phases okay. So now our lineage works appropriately for a case. And then, of course, obviously, an empty case as well. So all 7 green. findFrom locates the node. Lineage walks the parents up. So now let's go ahead and let's actually trace us some real lineages. So let's say I want to know about the lineage for the lich. And so you see it goes from creatures of the hold to undead to corporeal and then to lich itself. Okay. So I could then, of course, do our lineage for our maybe Frostmaw. So you see that's creatures of the hold, beasts, giants, Frostmaw. You say lineage skeleton. Creatures of the hold, undead, corporeal, skeleton. So you can kind of see we can go through that. So for example, lich's lineage, creatures of the hold, undead, corporeal, lich, the root to leaf, the exact path findFrom took down, reversed from the parent walk up. Lineage beasts works as well if we want to grab a category here. Lineage beast. Or beasts, sorry. So then you see it goes creatures of the hold and then beasts as well. So it works on a category 2. Beasts is one step from the root. And if we try to do something else, we could say, well, if I may misspelled or did lineage goblin, we could see here goblin's not in McCown's catalog there. So we can try out different options here. So the goblin there is showing hey, Scrivener McCown never filed the goblin. That's the not found path that our code is taking there, which is going to return null pointer. Lineage returns just an empty path. It doesn't crash in that case. So, and one of the things in the lab actually for this floor will be adding goblin back there. But okay, so we see now that all that works. And here's the question that sets up the rest of the course here. When I typed lineage goblin and the tree said not in the catalog, how much work did that actually take? findFrom started at the root and it had to check every node. So in this case, it was like 23 nodes before it could be sure that goblin wasn't anywhere. And even for a hit, it checks nodes one by one until it stumbles onto the match. In this case, there's no shortcut because this tree has no order. A child could hold anything. The only way to know is to actually go look. Think back to floor 1. McCown's flat alphabetized list and binary search cutting it in half each step. This tree threw that away. For all its branching structure, searching it is no faster than scanning the old list, big O of N, every time. A tree shaped like data is not the same as a tree that helps you find data. So what's missing? Well, really one rule. if every node kept its children in order, smaller on one side, larger on the other, search could throw away half the tree at every step, the way binary search did. That rule turns this loose tree into a BST, or a binary search tree. And it is exactly what the next floor builds. You built the tree this floor. Next floor, you make it fast. So let's just take a step back and what changed here. So for 4 floors, we built lines, right? We did chain, stack, queue, structures with exactly one order front to back. This week, the shape branched, and with it came genuinely new ideas. A node with many children, a parent pointer to walk back up, and the fact that one tree has more than one order depending on how you walk it. But notice what didn't change. It's still pointers and recursion, the same base case then recurse skeleton that we wrote several times. And then, of course, the last floor and then the floor before that. So it's a new shape, but old discipline. And one thread to carry forward through all this. The recursive destructor in deep copy you read at the top of the tree header file, this module was provided, so you could study the shape. You're going to actually write that in the next floor, because a binary search tree owns its nodes exactly the same way. So I hope this was helpful, and I look forward to seeing you in the binary search tree floor. Time to sally forth, adventurers. I'll see you soon. Bye-bye.